This screencast is going to talk about two types of reactions that we'll commonly encounter in this course. The first is metathesis reactions, otherwise known as double replacement reactions, and acid-base neutralization reactions, which are sort of a special kind of double replacement. So these two reactions, or in general, the kinds of reactions we're first going to talk about are precipitation reactions. And those reactions are those in which you mix two aqueous solutions usually, and it results in an insoluble precipitate, which is a solid or liquid in the case of, or an insoluble product, a product that does not dissolve in water. It's not an aqueous solution. So let's define some words here. The first is the word soluble, or solubility. Solubility is defined as the amount of a substance at a given temperature, so it does depend on temperature, that can be dissolved in a given quantity of solvent at that same temperature. So notice the temperature thing. You may know that solubility depends on temperature because think about trying to mix sugar into cold iced tea versus hot iced tea. It mixes much faster into the hot iced tea because it's more soluble. The heat actually makes it easier to dissolve. So temperature does matter. Solubility is changed based on temperature, and that's important to note. For insoluble, that means that it cannot be dissolved, and we're going to say that the amount that qualifies as insoluble is less than 0.01 moles per liter solution. So you'll notice that's a very familiar unit. All right, so for an example of a solubility might be the fact that lead 2 iodide, dissolves in 1 liter of water. So 1.2 times 10 to the negative third moles of that dissolves in 1 liter of water of H2O at 25 degrees Celsius. Okay, so that's a solubility. That's an example of a solubility. Insoluble would be less than that number I just gave. Why are certain things insoluble? We've talked about why certain things are soluble. For example, ionic compounds, the attraction, the water is able to dissociate them. But why might something be insoluble? Mainly what we're going to be dealing with is situations where the attractions between the ions are too strong. So the attractions between the ions are stronger than the water that tries to pull them off. So the water's attraction is not strong enough, basically, to separate those ions. Okay, so there are some rules that you'll need to know for the AP, and there's really only one solubility rule you need to know for the AP. There are other rules, but this is the only one the AP expects you to know without being able to look it up, and that is that sodium, potassium, ammonium, and nitrate ions ions made from these things are all soluble, okay, in water. So when you have these ions in a compound, like for example the compound ammonium phosphate, you'll notice this compound has the ammonium ion in it. This is going to be soluble. Barium nitrate. And for nomenclature practice, I suggest you try to write out the formulas for these from memory. Barium nitrate has a nitrate in it, so it is going to be soluble. All nitrates are soluble. But for example, let's say you have cobalt 2 hydroxide. That would be insoluble, according to these rules. Okay, so why do we need to know about solubility and this? Because this is going to help us predict a product of a precipitation reaction. Let's look at an example. This is a metathesis sometimes called a double displacement. Okay, here's an example of a metathesis reaction. And see if you can write this out from memory. Lead to nitrate reacts with potassium iodide. Okay, potassium iodide. So in a metathesis reaction or a double displacement, you're going to have two ions that are switching places, and those are the two positive ions. The general form of this is AX aqueous plus BY yields AY plus BX. And one of these, if the reaction happens, is a solid precipitate. The other is soluble. So in the case of lead to nitrate, which you should have been able to write, but it is PbNO3 aqueous plus potassium iodide, Ki aqueous, we're going to yield two products. One of those products is going to be lead to iodide, and that, we don't know if that's solid or aqueous yet, and potassium nitrate. Looking at these two, one of them has to be a solid and one has to be aqueous. Well, since the potassium nitrate has one of those ions that I talked about earlier, nitrate, we know that's going to be aqueous, and the lead iodide is going to be solid. So the lead iodide is our precipitate, which is abbreviated PPT, kind of like PowerPoint. Now, this is not a balanced chemical equation, so see if you can balance it. And if you want to pause, do that, but I'm going to go ahead and show you that the balanced reaction, 2 here, 2 here. So this is now a balanced reaction. When I write it this way, this communication, this symbolic, is called the molecular equation. There are two other ways that we communicate these kind of reactions. The first is called a complete ionic equation, which I might call the CIE, complete ionic equation. So in this kind, you write them out as ions. So let's look at the ions here. We have a lead 2 plus ion, aqueous, plus 2 nitrate ions, aqueous, plus 2 potassium ions, plus 2 iodide ions. And that yields, and I'm going to kind of drop down a level because I've run out of space, or maybe I'll just shrink down a little bit here. There we go. That yields PbI2 solid, because that's not an ion, plus 2 potassium ions, plus 2 nitrate ions. And these two are aqueous. So this is called the complete ionic equation because it shows all the ions and what they're doing. So we kind of separate out the ions. I've separated out the lead and the nitrate, the potassium and the iodide, but when it's a solid or a liquid, or sometimes a gas, you'll write it as its compound and then leave the other two ions. There's one more step that you'll generally be asked to do, and that's to write what's called the net ionic equation. And in this equation, you're going to basically cancel out things that are the same on both sides. So looking at this equation, we see that the lead does not remain the same. The nitrate does, though. There's 2 nitrates per side, so we cross those out. 2 potassiums per side, and cross those out. Now the iodide becomes part of a thing. So the net ionic equation here is Pb2 plus aqueous plus 2I minus aqueous yields solid PbI2. This is your net ionic equation. Basically, it's showing you the things that actually changed, the reaction that happened. You had aqueous lead combined with aqueous iodide ion to make solid lead to iodide. These things that I've crossed out up here that are the same on both sides are called the spectator ions, and they're called that because they're spectators. They're watching. They're not participating in the reaction. Much like when you go to an athletic event, you're the spectator. If you're in the audience, you're not participating. All right, so let's look at what we can do with this. Another example of writing a net ionic equation. We'll do lots of practice with these equations. Let's see. Let's start with an aqueous solution. So this is an example problem that I'd like you to solve for class tomorrow as a practice. An aqueous solution of barium chloride and is added to an aqueous solution of sodium sulfate. So you need to do the following things. The first thing you need to do for class tomorrow is write the balanced equation. Balanced molecular equation. Okay, so predict the products, predict which one's going to be soluble and which one's going to be insoluble. And then, once you've done that, you need to write the complete ionic equation. And the third thing you need to do is write the net ionic equation for this example. So following the example I gave above, I'd like you to come to class tomorrow with a complete ionic equation and the net ionic equation written for this example problem. Moving on from there, so you can pause and do that now or come back and do it later, but it needs to be done for class. Moving on from there, what are we going to use this for? Well, it turns out we use this in stoichiometry. This is called stoichiometry of aqueous solutions. So here's a problem. Let's work through a problem and you can see how this is used. So I'm asking this is going to be example 2. How many grams of silver chromate will precipitate when 150 milliliters of 0.500 silver nitrate, molar, are added to 100 milliliters of 0.400 molar potassium chromate. So this brings together several skills. You're going to have to understand how to convert from molarity, concentration to moles. You're going to have to do a balanced chemical equation where you predict the products, and you're going to have to be able to determine the limiting reactant and solve for that, how much was using that limiting reactant. So let's go through this. This is good practice in a lot of cases. All right, so silver chromate will precipitate. That automatically tells us that our solid is going to be silver chromate, which is convenient. We don't have to remember any solubility rules there, but we should look at it and know that whatever one has the nitrate is going to be soluble. So let's write first our balanced equation. Okay, so we know we are reacting silver nitrate, which is AgNO3. Remember, Ag is a +1, NO3 is a 1-, so combining those, we get AgNO3 aqueous, to potassium chromate. So potassium chromate is going to be a K+ ion plus a CrO4 2- ion. So that's going to give us a formula of K2CrO4. That's potassium chromate. That's an aqueous solution. It's going to yield silver chromate, so Ag2CrO4, solid, which we know from the problem, and potassium nitrate, which if we weren't given the information of which one was the solid, we would know the potassium nitrate is the aqueous because it has nitrate in it. So next, we're going to need to do all of our steps that help us determine the limiting reactant and predict the amount of product. I'm going to show first the BCA table way, and then I'm going to show the alternate method where you do the stoichiometry all the way across. Okay, so if you don't care about the BCA table way, you could fast forward until you see me done with it, with my answer squared, and just watch the part with the alternate method. If you are really wanting to think hard about how those two methods fit together, it might be a good mental exercise to build your understanding, to try both ways. So when I balance this, I get that 2 silver nitrate, moles of silver nitrate, aqueous, plus 1 mole of potassium chromate, aqueous, yields 1 mole of silver chromate, solid, and 2 moles of potassium nitrate. That's my balanced equation. All right, so I'm going to do my BCA table, before, change, and after. And BCA tables, remember, have to be in moles. You can't just go straight to grams or leave milliliters. So let's use the information that we have here. I'll move this over just a little bit. We know that we have 150 milliliters, which is 0.150 liters of silver nitrate. I need to get that to moles. Well, the concentration of silver nitrate will help me do that. So I will take that concentration, 0.500 moles per 1 liter, and my liters cancel. And I know that I have 0.075 moles of silver nitrate. And that goes in right over here, 0.075 moles. Next, I need to convert my 100 milliliters of 0.4 molar potassium chromate. So 0.100 liters of potassium chromate times the fact that there's 0.4 moles of that per 1 liter gives me that there are 0.04, and that's 3 sig figs, that's 3 sig 4, 0 moles of potassium chromate. At the beginning, I have 0 moles of the products because the reaction has not occurred. All right, so my next step is to try to determine my limiting reactant. My pattern is always to start with the silver, the one furthest to the left. So I'm going to say if I used up all of my silver nitrate, how much potassium chromate would I need to use? So I'm looking at that minus 0.075, so I know that 0.075 moles of silver nitrate is to X moles of potassium chromate as, I'm just going to slide over here, I'll come right back. Whoop, I need to look at my balanced chemical equation. Come on. Whoops. Touchscreen is not happy. All right, so 0.075 moles of silver nitrate is to X moles of potassium chromate as 2 moles of silver nitrate is to 1 mole of potassium chromate. So I've gone through and looked at this mole ratio here, 2 to 1. If I use up all of my silver nitrate, that means I will have used up 0.0375 moles of potassium chromate. When I put that here, I find that I have 0 of the silver nitrate left, 0.0025 moles of the potassium chromate left, and that tells me that silver nitrate is my limiting reactant because I have an excess of potassium chromate in this case. If for some reason you had started with the potassium chromate and found that you didn't have enough silver nitrate, you'd have to go back and redo that calculation based on the potassium chromate numbers. So looking at back over here, I can fill in the changes in my other two because I see that potassium chromate to silver chromate is a 1 to 1 mole ratio. So this is going to add 0.0375. And then my silver nitrate to potassium nitrate is a 2 to 2 ratio. So they should be the same, 0.075. So in the end, I'm going to have made 0.0375 moles of, I should actually label all of these, of silver chromate. And I'm going to have made 0.075 moles of potassium nitrate. What I care about is the 0.0375 moles of silver chromate because I've asked how many grams of silver chromate will be precipitated. So my final step in this is to take that 0.0375 and notice I've gone out past the number of sig figs I need because I'm just carrying out some extra figures until I round at the very end. Moles of silver chromate, and then I'm going to turn that into grams of silver chromate. That's 331.74 grams of silver chromate, which gives me a total of 12.4 grams silver chromate produced. All right, so that is one method for solving this problem. The alternative method is to just do the stoichiometry conversion all the way across and then pick which one for both of them and pick which one is the limiting reactant at the very end. So let me show you that method. So you would start with your 0.150 liters of silver nitrate, because it said 150 milliliters, so I just converted that. Convert that then using your concentration. There's 0.500 moles of silver nitrate per 1 liter of solution. So my liters are going to cancel. Then I know that from the stoichiometry, there's 1 mole of silver chromate per 2 moles of silver nitrate, silver nitrate. And then finally, so I've done moles of silver nitrate to moles, I need to convert this mole of silver chromate to grams. And that gives me an answer of 12.4 grams of Ag2CrO4. Now, having done the problem previously, I know that that's my limiting reactant, but if you just did this approach, you would need to go and show then that the other one was in excess. So 0.100 liters of potassium chromate, and I'm going to carry the stoichiometry across. One mole AgCrO4 to 1 mole of potassium chromate times the molar mass. And canceling my units, liters cancels liters, moles of potassium chromate cancels moles of potassium chromate, moles of silver chromate cancels moles of silver chromate, and I'm left with 13.3 grams of silver chromate. And the one that makes the least amount of product is the limiting reactant, so here is my limiting reactant. It's silver nitrate. So that's an alternative method. If that method makes sense to you, use it. If the BCA table makes sense to you, use that. Either one is acceptable as long as you show all of your work and your units cancel to get you the right unit. So that's an example of how we will do stoichiometry with solutions. And that is a pretty good stoichiometry problem there. Okay, so you could have just done this to answer that problem, or if the BCA table helps you organize yourself, you can use the BCA table. Now, let's look at the second type of reaction I wanted to talk to you about, which are acid-base neutralizations. First, we need to define acids and bases. We defined, earlier you probably defined acids using the, so the different definitions of acids. One you might be familiar with is the Arrhenius, which I think I spelled correctly, definition, which says that acids are things that give up H plus ions, and bases give off OH when they're dissolved. We're going to be using in this course the Bronsted-Lowry definition, which says that an acid is a proton donor and a base is a proton acceptor. We'll get more into this when we get more into acids and bases, but you need to know this definition. The Bronsted-Lowry definition is that acids are proton donors and bases are proton acceptors. Arrhenius' definition splits them off into what ion they give off when they dissociate. So an acid would be something that has an H plus ion, and a base would be something that gives off an OH ion. But we're going to stick with the Bronsted-Lowry definition. And neutralization reactions are reactions where you put an acid and a base together and they form a salt and a water. Okay, so it's like metathesis because you're kind of sort of doing a double replacement. So let's look at that. For example, one acid, hydrochloric acid, when we put that together with a base, sodium hydroxide, we see that it will make NaCl and water. Now the NaCl, it's got sodium in it, so it is aqueous, but the water is a liquid. It's not a dissolved substance. So there's sort of like your precipitate. Okay, it's not a solid, but it is a liquid substance. So when we look at the complete ionic equation of this, we have H plus Cl minus plus Na plus OH minus yields Na plus Cl minus plus H2O. Liquid, aqueous, and all the rest of these are aqueous. So then the net ionic equation becomes, we look at the Na is gone there, Cl is gone, so we end up with a net ionic equation of H plus aqueous plus OH minus aqueous yields H2O liquid. Okay, that is it, a salt and a water. All right, so how might we do a neutralization reaction? An example of that, building in your stoichiometry, is this question. So use the stoichiometry you had. This is example 3. I'd like you to solve this and be ready to do it in class tomorrow. Use the same process that we use in other stoichiometry problems. So see if you can extend that to a neutralization. The question is, how many milliliters of 0.610 molar sodium hydroxide solution are needed to neutralize 20 milliliters of 0.245 molar sulfuric acid. Notice this is not a limiting reactant question because you're not given 2 amounts of reactants. I'm specifically asking you how much of this reactant do we need to neutralize this much. So this is a straight up stoichiometry problem. There's no limiting reactant involved here. So see if you can do your stoichiometry conversions to find out how many milliliters of sodium hydroxide we need to react and neutralize 20 milliliters of sulfuric acid. And we will go over the answers in class.